Hello and welcome to another YouTube video on calculus. Hard to believe that we're almost already done with chapter 2, but we are right about there. In today's video, we're going to be going over topic 2.8, derivatives as a function. This is a very similar topic to yesterday, where we're dealing with the derivative, where we were dealing with the derivative at a certain point. But today, I want to suppose that what if we didn't have a fixed point and we wanted to be able to evaluate it anywhere? Well, recall the derivative of a function at a fixed point a is f prime of a is the limit as f of a plus h minus f of a all over h approaches 0. Well, if we want to be able to evaluate a function's derivative at any point, let's, instead of using a fixed value a, let's use a variable x. So what we're going to say is f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Well, what do we do with this? We have two variables, but here's the thing. This variable, theoretically, is just a constant when evaluating the limit. So all we need to do is evaluate like we normally do. So let's try it. So we really are going to be looking down here at this y. So another notation that we might use is y prime is equal to the limit as h approaches 0, and we're just going to want to plug in this x squared plus, this x plus h for this x squared plus 2. So we get x plus h, square it, minus the function that is going to be x squared plus 2, so minus 2, all over h, and I kind of forgot a little plus 2 over here. Now this 2 and this 2 cancel, which makes this a bit easier early on. Let's expand out this square, so we get x squared plus 2xh plus h squared minus x squared all over h. Well, what can we cancel? We can cancel these x's, and we're left with only h's, so what we get is 2x plus h. We're going to cancel, and that's how I got that, and we want to take the limit as h approaches 0. So now, as h approaches 0, this is going to go to 0, so we're just left with 2x. So y prime is really just equal to 2x. Interesting. So that supposes that a derivative of a parabola is a line. Very interesting. Another notation that we might... So I think it's important for us to know all the notations for a derivative. And there is quite a few. You may recall from yesterday that the first notation we learned was f prime of a, which in this case we're going to call x. Well, I introduced us to another one, which is y prime. Then another one that we have is dy dx. We also have df dx. We have d over dx of f of x. And then we have d f of x. And we also have dx f of x. So all of these expressions are the exact same, but I really just want to take a moment to highlight this derivative operator. So this right here is what we call the derivative operator. And it comes from this notation dy dx. Well, who derived this notation? This notation is called Leibniz notation. I will yeah, I'm already starting to butcher his name. Leibniz. Very, very credited mathematician. And this is actually an interesting fact for you. Newton and Leibniz both invented calculus independently. But what this notation really supposes is it's how he did the limits, which is the limit, as the change of x approaches 0 of delta y over delta x, which is really just change in y over change in x. Well, we don't want these to be equal to 0, so what he really defined for us was a new notation, which was dy dx, which really supposes as this is a very, very, very small number. Small number. Infinitesimally close to 0. And this is the change in y that corresponds to that change in x. So that's just kind of... Leibniz was very thoughtful of how his notation worked. If I remember correctly, Newton's original notation was with, like, dots representing the derivative. But Leibniz had this very intricate way of thinking and making sure that his notation was understandable. So all of these notations above are like derivatives. So, let's see. The next thing I really want to talk about is its connection to continuity. You may recall that a continuous function is a function where its limit as x approaches a of f of x is really just equal to f of a. If this is true, then the function is continuous. Well, a derivative is in fact, in order for a derivative to exist, a function must be continuous. So the reason for this is we're dealing with limits. A derivative is a limit. Dy dx is really the limit as h approaches 0 of f of x plus h minus f of x all over h. This is a limit. So suppose that we have a point x. Well, this function needs to be continuous for us to be able to evaluate the limit. If it's not, let me draw another example over here. Let's say that this function somewhat resembles this. If we try to evaluate this limit, well, the limit as x approaches, well, the right-hand limit does not equal the left-hand limit. So the derivative cannot exist at this point, because as x approaches this value, f of x plus h approaches this value x, it's going to be approaching two different numbers entirely. And as thus, the limit cannot exist. And we actually have something that we're going to call that, and I'm going to go over that in a moment. But I wanted to real quickly go over when can a function fail to exist. Well, let's start out with a corner. And the best example of a corner point is the absolute value of x. Well, if we wanted to evaluate this function's derivative at x, and I'm going to actually kind of make this a actual defined function, so we're going to call that 2. So we know that this function is really just x minus 2 is y. Well, if I want to take the derivative of that, we're going to call this a piecewise function. So we're going to call y is equal to all of this. So it's going to be equal to x negative x plus 2 for x less than 2, and x minus 2 for x greater than or equal to 2. Well, I'm also going to find one more point just to make this incredibly clear, that at x is equal to 2, x is 0. Well, if I want to evaluate the limit of this function, or find its derivative, well, the derivative of y prime is going to be the limit as h approaches 0 of x plus 2, x plus h plus 2 minus, or rather, this needs to be the absolute value, minus 2. There we go. Minus absolute value of x minus 2 all over h. Well, the way we will evaluate this is we have to break it down. So we're going to say y prime, and we're going to take the left-hand derivative, so is going to be the limit as h approaches 0 from the right. Well, we're going to be really using these values that are going to be greater than 2. So we're going to be doing x plus h minus 2. All right, minus, and what was I about to do? Oh, yeah. I think this example is just a small bit easier to do with a point, so I'm going to call this 2. There we go. So we have this point here, and f of 2, as we're going to say that we're going to evaluate this at 2, is going to be 0. And that means that this is also a 2. So that means all over h. Well, this 2 and this 2 are going to cancel. So y prime is equal to the limit as h approaches 0 from the right is h over h. That's just equal to 1. Okay, no problem. But now if we want to do the left-hand derivative, or take the limit from the left, y prime is going to be the limit as h approaches 0 from the left, and we are going to do, once again, evaluate at 2. So 2, negative 2, plus h, because minus h, minus 2, plus 2, is then put in the absolute value. Actually, no, that doesn't need an absolute value. I don't know why I want to keep putting absolute values in, just the way that most derivatives work. And then minus the value, which is 0, all over h. Well, this 2 and this 2 cancel. This h and this h cancel, but it leaves a negative 1. This limit does not exist. The limit as h approaches 0 of y does not exist. As thus, this derivative does not exist if it's a corner. So that's the first method. I want to kind of shrink this down so you can still see. Nope, give me a moment. Alright. So, there we go. That's a bit more manageable of a size. That's a corner point. But what about a discontinuity? Well, let me sketch a discontinuity graph. And this time, I think, because of our last example, you should be good to understand that, once again, this limit does not exist. This function is not continuous at the value. In fact, because of that fact, the limit does not exist, this derivative does not exist. So this derivative does not exist. And I'd recommend you write down derivative does not exist at at discontinuities. Continuing on, we now have a vertical tangent. So what this really looks like, if my why is this being like this? Alright, well this is an example of a vertical tangent where this point near 0 is almost completely vertical. So what this really means is the limit is going to approach infinity. So the limit as f of x plus h minus f of x all over h as h approaches 0, this is going to approach infinity or negative infinity. And because of that, we say the derivative does not exist, as infinity is not a number. The final example is cusps. And cusps, like a vertical tangent, drawing one in here, what really happens at a cusp is, as we approach this from the from the left, apparently I don't know my lefts from my rights, the function is going to approach, or the limit as h approaches 0 from the left is going to approach negative infinity. But as it approaches it from the right, the limit is going to approach positive infinity. So this limit, it does not exist since the limits don't equal each other. So I have 5 examples here that I'd like us to work out, and I'll give you a moment if you want to take your guess. My question is, which of the following is differentiable at all real numbers? Well, let's go through these. This first one is a discontinuity, so it's not continuous at this point, as thus it's not differentiable at that point. So we know it's not A, because the limit as h approaches 0 from the left does not equal the limit as h approaches 0 from the right. Okay, the next option is a cusp. So it's approaching negative infinity from the left, but positive infinity from the right. So in this case, once again, the limit as h approaches 0 from the left does not equal the limit as h approaches 0 from the right. Or, in another word, you can write down the left-hand derivative does not equal the right-hand derivative. So it's not B either. So C has 2 corner points. So once again, this shows us that the limits do not exist, so we know it's not C. D is interesting. In fact, if you were to sketch a graph of this as like a derivative, you'll see that it actually almost identically matches this function. But I digress. So D is really going to be differentiable for all real numbers, because no matter what point I choose, the left-hand derivative and the right-hand derivative are going to approach the same number. They're going to approach the same slope even. This last one, E, is incorrect because right here it has another vertical tangent. Alright. Higher order derivatives. So what is a higher order derivative? A higher order derivative is, or let's ask this, why do we want to know the higher order derivatives? Well, it's going to be the derivative, the slope of the, this is going to sound very strange, but it's going to be the slope of the derivative function, which later on you'll learn is going to tell us the concavity of a function. So, what is a higher order derivative? Well, we just take d over dx of dy dx. It's the derivative of the derivative function. And what do we call this? We call this d squared, and what's it called? All over dx squared. So this is the second derivative of y with the respect to x. All right. Continuing on, I do have an example for us to work out. So we have a function is equal to x squared. So we want to find our df dx is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Let's solve that. So in this case, we have df over dx, or I believe I should probably be using the prime notation since this problem's asking it in prime notation. F prime is equal to the limit as h approaches 0 of x plus h squared minus x squared all over h. Well, that just evaluates down to the limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h. Well, this x squared and this x squared will cancel. This h, and that h are going to cancel. So we are just left with 2x plus h. The limit as h approaches 0 in that case then is 2x. All right, so we found the first derivative. All right, let's clean up our work. And now we have to do it again. I'm cruel. Very cruel. So now we want to find, and let's erase this. So this here is equal to our next derivative. So now we're going to take d over dx of f prime of x. And we know that that's going to be the limit as h approaches 0 of f of x plus h. So f of x plus h minus f of x all over h. Well, this is d. I'm going to simplify this notation. So this is f double prime of x is equal to the limit as h approaches 0 of 2x plus h minus 2x all over h. This multiplies out to be 2x plus 2h minus 2x all over h. The two x's cancel, and this h and that h cancel. So we're just really left with the limit as h approaches 0 of 2. So we are left with 2. All right, that one was a bit easier. Now on to the most certainly going to be the most difficult. So we have d over dx of f double prime of x. So what this is going to tell us is we want to take f of x plus h minus f of x all over h. So d over dx of f prime of x. Well, we don't have anywhere to plug in h, or x plus h, so it's just 2 minus 2 over h. That's 0 over h. So in this case, the derivative is 0. And that's actually an interesting fact. The derivative of every constant is 0. So I now have a few more challenging problems that I'd like us to do. So for this first one, we want to do d over dx of y is equal to the d over, not there yet, limit as h approaches 0 of 4x plus h minus 2 plus 4x plus 2. The 2's cancel off right off the bat. I'm going to just get them out of the way so I don't have to do as much writing. So our y prime in this case is going to be the limit as h approaches 0 of 4x plus 4h minus 4. All right. Minus 4x all over h. This 4x and that 4x cancel. This h and that h cancel. The limit as h approaches 0 of 4 is just 4. Alright. I suppose I should maybe... Nope. Not what I wanted to do. Okay. There we go. Select all of that. Move it over. Delete that. And then we finally get y prime is just equal to the constant 4. Continuing on, we now have f of t is equal to t squared minus 5t plus 1. Okay. So, what we're going to look at, so we want to take the derivative, dt. We're not going to use dx here. We're going to use dt since we're differentiating a function with respect to t, of f of t is equal to t, the limit as h approaches 0 of t squared, t plus h squared minus 5t plus h. And I'm not going to add in the plus 1 because we're going to subtract it off later, so I'm just going to leave it off. Makes my math a bit less complicated. And all of that's over h. I'm not going to worry about the limit immediately. We're just going to expand everything out. So we get a t squared plus t 2th plus h squared minus 5t minus 5h. Alright. And that should be a plus. And then minus t squared plus 5t. Alright. All over h. Let's cancel some things. This t squared and this t squared cancel. This 5t and this 5t cancel. And now we're just left with things with h's. So, now we just have to do... So now we just have 2th plus h squared minus 5h. 2t. Yep. Alright. And then we're dividing that by h. That h, that h, that h, and that h all cancel. So we are just left with 2t minus 5. And we take the limit as h approaches 0. I plus h. So then we're just left with 2t minus 5. Alright. And as we learned from the previous example, y prime, double prime over here is just going to be 0. I'm not going to show that using our limit. However, I bet you could probably do a bit of intuition here. If the derivative is a slope of a tangent line, and we have a line, well, the slope of that line, Rm, is just going to be the derivative. So, in this case, our f double prime of t is going to be 2. Alright, and then now I have to erase a ton of work. Not there yet. And this one I think is going to be the most challenging, so I'm going to do both the first and second derivatives. I'm going to delete that as well. I can care less. Alright. So, we want to know what is going to be... Oh, that was an h. So, what is h prime of t? Well, it's going to be the limit as h approaches 0 of x plus h cubed minus t cubed all over h. Well, then h prime of t is going to be the limit as h approaches 0 of, well, let's see what we can do. And also, I called that an x on accident. That needs to be a t. So, we are going to have t cubed, or actually, give me one moment. So, we are going to have, and this is a small bit of a doozy, t cubed minus 3t squared h plus, or sorry, not minus, plus 3 t h squared plus h cubed minus t cubed all over h. Well, this t and this t cancel. So we're now left with h prime of t is equal to 3, or the limit as h approaches 0, of h over h, because I'm factoring out an h, times by 3t squared plus 3t minus, 3th, and then plus h squared. Well, h prime of t then, because this is just 1, we can now just evaluate the limit. All of this stuff over here goes to 0, so we're just left to 3t squared. Alright, well that's a challenge. Now we have to differentiate this. So now we're going to have h double prime of t is equal to 3t plus h squared minus 3t squared all over h, and the limit as h approaches 0. Okay, so h double prime of t in this case is going to be 3t squared plus 6th plus h squared minus 3t squared all over h. Well, we can cancel the 3's, and now we just have to take the limit as h approaches 0 of 6th plus h squared all over h. Well, we can cancel that h, and that h, and this h is just going to go to 0, so we get 6t for a second derivative. Alright, continuing on, this is the last thing I have for you today. We need to sketch on the same set of axes the graph of the derivative of the function. So, I'll give you a moment if you want to try to do this on your own. So what I'm going to start out by doing for this farthest left one is I'm going to draw in 2 asymptotes. And the reason why is as you get closer and closer to this point on the circle, it's approaching infinity. Over here, it's approaching negative infinity. And over here, or actually, sorry, I got that backwards. Over here, it's approaching positive infinity, and over here, it's approaching negative infinity. And at some point in the middle, it's 0. So if we're sketching this graph, it's going to look something like this, almost like a tangent line. All right. Continuing on, we now have a graph of a parabola. Well, as we learned earlier, a derivative of a parabola is always just a line. So, and this one doesn't look to have any other x's in it, so I'm going to just say that this right here is about the derivative of a function. As over here, it seems to be increasing. Yeah, I believe this would be right. And finally, we have this function. It's once again an exponential. If we're looking at it, it looks like it's going to about grow at the same rate as said exponential, just maybe a small bit faster. So those are our 3 graphs. I hope you found this video informative and enjoyed, and I will hopefully see you all in my next video once we start going over rules of derivatives. Alright, hope you all enjoyed. Goodbye.